Hey everyone listening out there, especially all you higher graphic communication students. Getting ready for those exams, eh?
Big year coming up.
It is. And I know some of you might be looking at those drawing standards and thinking, oof, where do I even begin with all this?
Yeah, I get it. They can seem a bit intimidating at first. All those lines and symbols and rules.
Right, it's like learning a whole new language.
Yeah,
But don't worry, we're here to break it all down for you, make it clear, easy to understand, and, dare I say, even a bit fun.
exactly. And the good news is, once you get the hang of these drawing standards, they're actually pretty straightforward.
Definitely. It's like anything. Really, the more you practice, the more comfortable you become. And to help us on this journey, we've been digging through some pretty interesting stuff. The SQA course reports in the last few years.
Oh yeah, those course reports are gold mines of information. We've pulled out some really useful insights that'll help you understand not just what the standards are, but why they matter.
Exactly. And one thing that stood out to us is that students often struggle with those explain questions on the exam, especially when it comes to, yep, you guessed it, drawing standards.
It's one thing to know how to draw something according to the standards, but it's another thing entirely to be able to explain the reasoning behind those standards.
Right. Like, why do we use this particular line type for hidden detail?
Right.
Or why is dimensioning so important?
Exactly. So that's what we're going to focus on today, helping you not just learn the standards, but really understand them so you can nail those explain questions.
And we've got some great visual aids to help us along the way. We'll be referencing some helpful videos, which, as you might have guessed, breaks down all the different line types you need to know.
Yeah, seeing those lines in action can really help it all sink in.
Absolutely. Because let me tell you, getting those dimensions right is absolutely crucial.
Crucial. It's like the whole point of technical drawings is to communicate precise measurements. If your dimensions are off, the entire project could be compromised.
Imagine you're an architect designing a bridge, right? And your dimensions are even slightly out.
Oh, that's not good. That's a recipe for disaster.
Exactly. The bridge might not be structurally sound.
It could even collapse, all because someone didn't pay enough attention to dimensioning.
Okay, so we've established that drawing standards are important. But let's back up a bit and talk about why they exist in the first place. What's the big picture here?
It's all about communication. Think of drawing standards as the universal language of engineering and design.
A universal language.
hmm
So like, no matter where you are in the world, if you understand these standards, you can communicate your design ideas to anyone.
Exactly. It doesn't matter if you're working with someone down the road in Edinburgh or across the world in, say, Australia. Everyone understands the same symbols and conventions.
That's pretty amazing when you think about it. It's like this shared knowledge that connects people from all over the place.
It is, and it's been evolving for centuries. Did you know that the whole standardization thing really kicked off back in 1842 with a guy named John Herschel and the blueprint process?
Oh yeah, the blueprint process. That's where you coat paper with a special solution and then expose it to light to create a copy of a drawing.
Exactly. And it was revolutionary at the time because it allowed for accurate and consistent reproduction of technical drawings. Before that, everything was hand-drawn, which meant there was a lot of room for error and variation.
So the blueprint process paved the way for more standardized practices.
Exactly. And those practices continued to evolve as technology advanced. We went from hand-drawn blueprints to computer-aided design, CAD, and with those changes came the need for updated standards.
Which brings us to, drumroll please,
BS 8888.
BS 8888, our new best friend.
It might sound a bit daunting, but it's really just the current standard for engineering drawing here in the UK.
And the SQA expects you to know it. They mention it specifically in those course reports we talked about.
Yep. They want you to understand how to apply BS 8888 conventions in your own drawings. Things like line types, dimensioning, the whole shebang.
So it's kind of like the rule book for engineering drawing.
Exactly. It sets out clear guidelines to ensure consistency and accuracy in technical drawings.
And it's based on the work of the British Standards Institute, right?
That's right. They're the folks who develop and maintain all sorts of standards, not just for engineering, but for all sorts of industries. Everything from food safety to construction to, well, drawing.
It's fascinating to think about all the work that goes into creating and maintaining these standards, but it's obviously worth it because it ensures that things are done properly and safely.
Absolutely. Standards are there to protect us, make sure things are done right, and help us communicate effectively.
All right, so we've covered a lot of ground already. We've talked about why drawing standards are important, the history of standardization, and the role of BS 8088 in modern engineering drawing, but we've only just scratched the surface.
Let's talk building drawing symbols. Ever seen those on a drawing?
Oh, yeah, those are the ones that always make me think of, like, secret codes or something. All those squiggles and shapes, what do they even mean?
They're not secret codes, but they are a kind of language, a visual language specifically for buildings.
Hmm.
Each symbol represents a different element of a building, like a door, a window, you name it.
So it's like shorthand for architects and builders. Makes sense.
Exactly. They can convey a lot of information quickly and clearly without cluttering up the drawing with a ton of text.
So, wait, if I'm looking at a building drawing, how do I know what each symbol means? Is there like a secret decoder ring I need?
Haha, no secret decodering required. It's all standardized, of course.
Of course, it
No.
wouldn't be a drawing standard without some standardization, right?
Right. There's a British standard, just like with engineering drawings, that defines each symbol. That way everyone's on the same page.
Okay, that makes sense. Otherwise, you'd have architects and builders all speaking different languages, and that would be chaos.
Exactly. You don't want to mix up a window for a door. Speaking of things that can get a bit tricky, how about we move on to section views? Remember those?
Oh, yeah, section views. Those are the ones where you kind of slice an object open and show what's going on inside, right?
That's a great way to put it. Section views are all about revealing those hidden details that you wouldn't normally see from the outside.
So, like if you were designing a new phone case, a section view will let you show where all the buttons and the camera lens and the charging port go.
You got it. It's a way to show how all the internal parts fit together.
Cool. And you were saying there are different types of section views.
Yep. There are full sections, part sections, revolved sections, even stepped sections. Each one serves a different purpose.
Wow, that sounds complicated. Why not just use hidden detail lines to show what's inside? Wouldn't that be easier?
Sometimes, sure. But for complex objects, hidden detail lines can get pretty messy.
Ah, okay, I see. So section views just make things clearer and easier to understand, especially for those detail-oriented engineers.
You know it. And speaking of understanding things clearly, let's talk about third angle projection. Any idea what that is?
Third angle projection. Rings a bell, but I can't quite place it. It's something to do with representing 3D objects on a 2D surface, right?
Exactly. Think of it this way. You have a box, and you put an object inside.
All right, I'm picturing it. A box with something inside.
Now, imagine you shine a light through the box and project the object's shadow onto each side. You'd have a front view, a top view, a side view.
Oh, so that's how you get those different views of the object on a flat piece of paper.
Precisely. And the arrangement of those views is standardized third angle projection is what we use here in the UK. But it's not the same everywhere.
Oh, really? So what, like other countries use a different system?
Yep. Some countries use first angle projection. So it's important to be aware of those differences if you're ever working on international projects.
That makes sense. You wouldn't want to send your drawings to a manufacturer in, say, America and have them misinterpret everything because they're using a different projection system.
Exactly. Now, before we move on, let's quickly recap what we've talked about so far in this part. We covered building drawing symbols, which help us represent building elements efficiently, section views, which let us peek inside objects, and third angle projection, which is how we show 3D objects on a 2D surface.
Phew, that's a lot of information. But it's starting to make sense now. It's all about clear communication, isn't it? Making sure everyone understands exactly what's going on in the drawing.
You've got it. Clear communication is key. And you know what else is important? Tolerances.
Oh yeah, tolerances. Those are the ones that tell us how much wiggle room we have with measurements, right? Like how much a part can deviate from the ideal size.
You're on the right track.
They always seemed a bit mysterious to me.
Well, think of it this way. No matter how precise your CAD drawings are, when it comes to actually making something, there's always a bit of wiggle room.
Wiggle room. So you're saying things won't always be exactly the measurement I specify in the drawing.
Right. You can't expect absolute perfection in the real world.
I guess that makes sense. Manufacturing processes aren't perfect.
Exactly. There are always tiny variations no matter how hard you try to control things.
So our tolerance is basically a way of saying, it's okay if this part is a tiny bit bigger or smaller, as long as it's within this range.
Exactly. Tolerances define those acceptable limits of variation.
Okay, so how do you actually communicate tolerances on a drawing?
You use symbols and numerical values right there on the drawing to specify the acceptable range.
So instead of saying, this hole needs to be exactly 10 millimeters, you'd say something like, this hole needs to be 10 millimeters plus or minus 0.1 millimeters.
Precisely. And there are different types of tolerances depending on what you're specifying. Linear tolerances for length and distances, angular tolerances for angles.
And you mentioned something called geometric tolerances before the break.
Oh, right. Those are the ones that deal with the shape, orientation, and location of features. A bit more advanced, but super important for ensuring things fit together properly.
Okay, so I get that tolerances exist, and I kind of get how to specify them. But why are they so important? What difference does a tenth of a millimeter really make in the grand scheme of things?
Well, in some cases, it can make a huge difference. Imagine you're designing something with moving parts, like a gear system.
All right, I'm picturing it. Gears.
If the tolerances on those gears are too loose, they might slip and not mesh properly.
Ah, so the whole system could fail because of a tiny variation in size.
Exactly. Or think about something like a phone charger. The tolerances on the connector pins are crucial for making sure it fits snugly into your phone.
Right. Too tight and you can't get it in, too loose and it falls out.
Precisely. Tolerances are all about finding that sweet spot.
So it's a balancing act, making sure things fit together, but also being realistic about what's achievable in manufacturing.
Exactly. And it's not just about knowing how to specify tolerances. You need to be able to explain why you've chosen those specific values.
Oh, right, those pesky explain questions. They seem to pop up everywhere in SQA higher graphic communication.
They do. But remember, it's all about demonstrating a deeper understanding, showing that you've thought about the implications of your design decisions.
So it's not enough to just memorize the rules and procedures. You need to be able to apply them thoughtfully, like a tree designer.
Exactly. And those drawing standards we've been talking about, they're not just arbitrary rules. They've evolved over time to address real-world challenges and make sure things are designed and built safely and efficiently.
Right. It's all connected. It all matters.
It does. It's all part of this amazing world of design and engineering. And for all you SQA higher graphic communication students out there, remember, don't be afraid to dive into those standards, explore them, and really understand them.
They're your tools for clear communication, for bringing your ideas to life. And hey, if you ever get stuck, remember there are tons of resources out there to help you. Your teachers, online communities, even the course reports themselves.
Absolutely. Don't be afraid to ask questions and learn from others. That's what it's all about.
So to wrap things up, we've covered a lot of ground in this deep dive. Line types, dimensioning, BS 8888, building, drawing symbols, section views, third angle projection, tolerances.
Yo, that's a mouthful.
It is. But hopefully it's all starting to make sense now. Well, we've reached the end of our journey for today. Thanks for joining us on this deep dive into the world of drawing standards. We hope you found it insightful and maybe even a bit inspiring. Until next time, keep those pencils sharp and your minds even sharper.